This is, I believe, hopefully the last video. If I can fit it all in, it doesn't get too long. But it's about charging capacitors. So basically, what happens when we first turn on a circuit? What happens? How do capacitors act? What do they do? How do they charge? What happens when you discharge them? This will go along with some of what I was talking about down towards the end of, not the last video I believe, but the video before that, when we were talking about using a capacitor to level out when we rectified current, and so we didn't have the, so it was just a little bit of a bumpy road rather than the big arches that were going on that went all the way down to zero. So hopefully this will help finish clearing all of that up and how that works. So a few things: when you first turn on a capacitor, it has absolutely no charge on it, which means the very first bits of charge you first to throw on there, they have nothing to resist against them. So if you think about, say here's our capacitor, drawing it from the side. When I first start throwing negative charges on here, the first negative charge I have on here, well, this is neutral, so there's no resistance to me throwing that negative charge on there. But the next charge I try to throw on there, well, this already has this negative charge here, so there's a little bit of resistance for that one. And then the third charge I throw on there, now there's two negatives on there, there's a little more resistance. And then as I keep going and more negative charges get in here, more and more resistance builds up. And then eventually you get so many on there that whatever voltage you have doesn't have enough power, enough strength to it to actually add any more onto the plate, and it's full. But again, right at the very beginning, there's nothing on there, and the first charges go on there with little to no, starts off with no and then very little resistance. So at the start of charging a capacitor, it basically acts as though it has no resistance at the start. And if there's absolutely no resistance and there's nothing but your capacitor, you're basically going to get like an infinite current. So there's no resistance and you'll have a big current. Starts off real big, resistance starts off real low. As charge builds on it, it gets harder and harder to force more charges on there. So as charge builds, R increases. It increases, and the current decreases. It goes down because less and less charge can be pushed onto that plate, forcing less and less charge off of this side, which means the current will slowly trickle down because no more charge going on to here, no more charge getting forced off of here, right? Because as this side fills up, it would force these other little negative charges off that way. And so when it gets fully charged, as we just said, when fully charged, R basically goes to infinity. It's like it's 100% resistance, and I goes to 0. So we have no more current flowing, and the capacitor starts to act like it's an infinite resistor. And so if you think about this, the way that this would look is if we drew this graph out for a current, let's say. All right, current, what you're going to have is an exponential decay. So current as a function of time, and here I'm going to really struggle with this on this, drawing on this, but it's going to start at some point. You have your maximum current, and then this is when you have a resistor included so that it doesn't just go wild, and then this is going to curve down and go towards 0 as it gets out of here. If there was no resistor hooked on this, in other words, what you want to do is hook a resistor in line with your capacitor, because if not, then your initial current is going to be basically, for all purposes, right out of the gate, is going to be infinite. And that's not good. It's probably going to wreck your electronics or anything like that. It can be bad. So you usually want to include a resistor. So what we're talking about here, specifically like this graph, is called an RC circuit. It's a resistor capacitor circuit, and that's really what we're interested in, because having just a capacitor, not usually a good idea. And so we want an RC circuit, something like where we have a battery here or a cell, and then we have our little switch to turn it on and off, our resistor, a capacitor, right? Capacitor, trying to make that sure, and then connected over here to the battery. So this would be the battery plus minus. This is the capacitor with a certain capacitance. And you have something like that. And this is our switch. Close it and it starts filling up. So as soon as you close that switch, it starts with its maximum current and starts to just go down. This acts as though it's a short when you first turn it on. So really this maximum current here could be given to you from V equals IR, just using that. But from that point, it just immediately starts to drop because this starts off acting like it's nothing at all, like it's a short. But then as it starts to fill up, it starts to act like a bigger and bigger resistance, which means it starts taking up a whole lot of that voltage, which means it can't be pushed through anymore. Some other diagrams that go along with this for how this looks. Let me move this down. If we did voltage drops across the components, the voltage drop across the resistor here, across this resistor, let's go ahead and let's maybe make that red. So the voltage drop across that resistor is going to decay down. Because if you think about it, at first this is a short, so the entire voltage drop, this whole V, is all across that. But as this increases in voltage, or increases in resistance, I'm sorry, it's going to use up more and more of the voltage until it gets to the point that it uses up all the voltage. So for the capacitor, which I'll do that one in green, let's say, its voltage is going to start off at 0, and it's going to do the inverse of this. It's going to go up like that until it's taking up all of the voltage. And of course, this maximum where that one starts is equal to where this one is going to end up, where he's using up, the capacitor is using up all of the resistor. So this is the V drop on C, and this is the V voltage drop across the resistor. Okay, so that's what that one will look like, and it should kind of make sense. As this one goes, as this voltage goes up, it's using it all up. Remember, it has to be, whatever this is, say this is 12 volts, it starts off, this would start off using the 12, and then this would start off using 0, and then as this moved up to 1 volt, using across it, as it got its increase up, this would only have 11, then this would have 2 as it got bigger, and this would have 10, and when this got to 5, this would have 7, and when this got to 11, this would have 1, and when this gets to 12, and it gets that infinite resistance using it all up, this would go down to 0. So that curves down towards 0. I know mine kind of looks like it's going up there a little bit. Another one we could look at is charge on the capacitor. I'll try and keep that on the screen there. Charge on the capacitor as it fills. Well, you're going to start off with 0 charge, right? It's going to start off at 0, and then it's going to increase exponentially. So it's going to be the same shape as the voltage, because as that charge goes up, it starts using up that voltage, so we have it doing that. All right, it's going to go up like that. That's charge on a, this is again still charging a capacitor. This is what happens to the voltage. Now, what we could do is change out the resistor, put a different resistor there, and I'll show you how that would affect these graphs. So for the current versus time, if we change out the resistors, a low resistor, a low R, is going to allow for a lot of current at the start, and it's going to trail off quickly as the capacitor fills. So that's for a low R, this guy. For a higher R, I'll probably change colors here, that you're going to start at a lower current initially, because the bigger resistance is going to make you have a lower current. But it's also going to fill that capacitor up more slowly, so it's going to go down towards 0 more slowly. It'll start below it, but then end up above it, and it'll eventually come down here and go towards 0. This is for a high resistance, a high resistor in the RC circuit. And then for current, the current, right, let's do what happens to the current the current with the same resistor, same resistance, the same resistor, but we're going to change out the capacitor. Well, if you think about the same resistor, at the start they're both going to have the same current going, because the capacitor is going to act like a short at the beginning for both of them. But the one with the low capacitance is going to fill up quickly. It's going to fill up very quickly, and so this is going to drop right down to 0 really quickly. That's with a low capacitor. And the one with a high capacitor is going to take longer to fill up, and it's going to, come out along this way and take much longer to reach 0 and fill up. So it takes longer to fill with the high capacitor than with the low capacitor if you have the same resistor there. And so they start with the same current. They both start off as shorts. Both the capacitors start off acting like shorts, so the current is based entirely on R. So they start with the same current. It's just after that, this one will fill up real quick and its resistance will go up real fast, so it'll drop the current to 0 real fast. This one's going to fill up more slowly and drop the current to 0 much more slowly. Okay, so that's it for, really, this was all for charging capacitors. Now, what happens when you discharge them? Well, essentially what's going to happen is the opposites of these things. So let's go down here a little bit. Let's do discharging. So discharging capacitor, what's going to happen to the voltage drop across the capacitor? So this is across the capacitor, not across the resistor. Well, what's going to happen is, as you discharge it, the capacitor is going to provide you its full voltage, whatever it was charged with, and then it's going to, as it discharges, drop off to the point that it's providing you nothing. So this would be the voltage versus time that you would get, the voltage across the resistor. As its voltage drop, its resistance will also drop as well. What about current? The current for this, for this graph, which is just V over R, it's going to also drop down. It's going to start off giving you that maximum current, and then it's going to exponentially decay until it eventually goes to 0, because you're going to start off where it has a bunch of charge to give you and a high voltage. As the voltage drops and the current drops, it's going to, or as the voltage drop and the charge available drops, the current's going to decrease. Okay, so the voltage drop and the currents are going to kind of mirror each other. And if you notice, again, this is still just these exponential decays. These are all exponential graphs. They're exponential decays there. And so what we can do is actually model this. This is a little bit of differential equations I'm going to show you here. Just real quick off to the side, if you learn this kind of stuff later, then you will appreciate this a little more. Go back and watch it. But basically we have dq dt, so if you learn this, this is the derivative of charge versus time, so this is basically an instantaneous current, is equal to a negative of a constant times the total charge on there, and that should make sense. The current is going to do the opposite of the charge. As the charge builds up, the current's going to drop. So it's very similar to our Hooke's law, but in Hooke's law, it was a second derivative here rather than a first derivative. So the solution to this is a little bit different, and so you have to ask yourself, if you've learned derivatives, what can you take the derivative of that gives you a constant and a negative out in front, but gives you back what you have? What do you take the derivative of, gives you what you had before with just a negative out in front of it? And if you've learned this at all, you know that if you take the derivative, d dx of e to the x, you just get e to the x, the exponential, right? Well, if you take the derivative, d to the x of e to the negative x, you're going to get, if you use the chain rule, you get negative e to the x. And so it turns out that this kind of a solution, this e to the negative exponential, is what we want. And so what we want here is actually, we're going to use q now, getting away from this. Q equals Q naught, some initial charge, times e to the negative k t. T is our function of time. This has to be a function of time. We're taking the derivative with respect to time, and that's our independent variable. And if you go through and actually solve this out, we can get dq dt. Well, what you have to do is use u substitution, like I just talked about before. U equals negative kt, and then this gives us that du equals negative k dt, and now I can substitute kt becomes u. Oh wait, actually I'm sorry, I want to do du dt. I'm going to take the divide that over. I've got negative k, right? I'm running out of room here. Move this down. Just remember those exponential graphs. Now I can substitute this stuff in. I will have and then of course chain rule. dq dt is equal to dq du dt. And it's like the du's cancel, and that's dq over dt. So that's what we're going for here. So I can say q equals, and do my substitutions, q naught e to the u. And now I can take the derivative of this with respect to u. And so this is dq du is equal to q naught e to the u. All right, but dq dt is dq du times du dt, and du dt is right here. So if I take dq du, this, and multiply it by du dt, so I have dq du and I have du dt. If I multiply them together, I'll get dq dt, which is what I want. So dq dt is dq du q naught e to the u times du dt negative k. And I'll have here, and then I'm going to go ahead and substitute back in because u is negative kt. I'll have dq dt is equal to negative, what do I want this? I want this as negative q naught k e to the negative kt. Okay? And so there you go. There's a nice little derivative of this. Derivation of it, and then we have to kind of figure out what k is and all that kind of stuff. But anyway, there you go. Nice little version, shows you that if we take the derivative of this, so in other words, if we start with this as q, right, we start with this as q, we take a derivative of it, look what we got. We got the original thing. Let me rewrite it one more line. We have a negative k and then a q naught e to the negative kt. So this part is the original, that's what q is, q naught e to the negative kt, and then we got this extra negative k out in front. And if you look up here, the derivative of it is this negative k times the original. And that's what we got. So when we take this derivative dq dt, we get negative k times the original of what we had. And that works. So just a little proof for you. If you learn derivatives and stuff, come back and look at this if you haven't yet, and it'll make sense. If you have already, then it should make sense. You see that this is a solution to this equation. It does work in there. You don't have to actually know this for your exam. It's just a little extra stuff. So we're going to use that. This is our solution. Q equals Q naught e to the negative kt. There we go. All right, so I'm going to put a box around that again. There we go. That's our big thing. It turns out, I'm not going to go through this derivation here for you, but we need to know what k is. And it turns out that k is actually equal to 1 over rc. I think I wasted enough time going through this derivation. I'm going to just give you this, which tells us then that rc, if you look about this, this has to be in units of 1 over time, because we're taking the exponential of something. This is already charge. This is charge. That means e to an exponential has to have no units, which means that And it's the same thing as taking like exponentials along with sine and cosines. This can't have any dimension to it because we already have all our dimension and everything like that, and we don't want the exponential of a dimension. So k has to have the units of time. And so that means, and if you look at it, if you do r times c, that actually gives you, or I'm sorry, k has to the dimensions of 1 over time. So this has to be a 1 over time, and it turns out that this does, r times c does have the dimension of time, and we call it tau, the time constant for this. It's the time constant for your circuit. Okay, and we'll talk about what exactly it's the time for in just a minute, but I wanted to just go ahead and show you, if you go through and, well, I'm not going to show you, just you go ahead and do it. It's a good exercise for you. Take the units for resistance, ohms, put them into their base units, and for coulombs, multiply it all together, and you should get a unit of time out of it. So give that a try and see if you get it, because of course, remember V equals IR, so R is V over I, right? And so I has that unit of time in it, and charge and everything like that, so you should ultimately end up with a unit of a time. And so taking this, we can do a similar thing. So we've got the Q naught here. I'm going to just we've got this Q naught thing. Let me move this down. All right, I'm just going to, instead of rewriting it, I'm going to put this right here. Okay, and we've got this. And similarly, you can go through with the same kind of decay graphs, and you've got this. I equals I naught e to the negative, and now we're going to change this. I should have changed this right here. Sorry, I just moved it down, didn't think about this. We're not going to use k anymore. We figured out what k is. It's going to be negative t over tau, and this is also negative t over tau, the constant, the time constant, RC. Tau is RC, right? And then we can also have one for voltage. You can do the same thing with our exponential decaying voltage as we discharge this, is V naught e to the negative t over tau again. And so these three equations, I believe these are the ones you're actually given in your data booklet. Double check to make sure I'm right. But these describe decays. Okay, this is either, we also had some things, if you look back here, this is for, just think of these as just for decays. Now, in discharging, we have this decay and we have this decay. So this would fit for, those equations would work for the voltage during discharging and the current during discharging. But during charging, we had some decay stuff too, like the current through the whole circuit through charging. So if you look at that, we've got, this is the current coming from the capacitor while we discharge it. This is the current through the entire circuit while we're charging it, through the RC circuit. So that equation will work for either one of them. It'll also work for the voltage drop across R. So any of these exponential decay things, those equations will work for. What about these? What about our growth ones that grow up like this? They're just the inverse of these other ones, essentially. Well, not really the inverse, more like the additive inverse of them. And what we can do is we have this one. These work for decays, for decaying values, and that's either during charging or discharging. You have to think about whether or not it would be increasing or decreasing. So that's for charging or discharging. For when it's increasing, when it's not decaying, but rather when it's growing, if you think about the growth of it goes towards a maximum value, right? Rather than starting at a max and going to 0, it starts at 0 and goes to a maximum. So what we can do is if we say, all right, this is Q naught for the exponential decay, it's the maximum. Well, if I take Q naught and subtract off this exponential decay, what am I going to get? Well, at first I get my exponential decay is Q naught at the start, so I take Q naught and it's minus Q naught. That gives me 0. As this decreases, I'm taking less and less away from Q naught, so my result grows and grows and grows. So for this more like exponential growth kind of thing, this reciprocal of it. So this is for decay. For growth, right? For growth, as it increases for these capacitors, what we can say is, like, for the charge across a capacitor as you fill it is Q naught minus Q naught e to the negative t over tau. Okay, that's a tau. All right, it's that minus it. You can then go ahead and factor out that Q naught, and it's Q naught 1 minus e to the negative t over tau, because it's just this Q naught, this line up here, and then you subtract off the exponential decay, and you've got the growth. All right, and when this eventually comes over here, when our exponential decay reaches 0, our growth is going to start to equal Q naught. So it gives us this right here for growth. I don't believe you're going to be given this one, but if you think your way through it, I think you're given this one. You can very easily just come up with this one. Maybe I'm wrong and maybe you are given this one. Double check and see which ones you're given so you know in your data booklet which ones you need to remember. But you don't really need to remember this. You should if you understand how it's just the maximum minus the decay version. It's very easy to come up with those very quickly. And then you can do the same sort of thing for current and voltage. So I is going to equal I naught 1 minus e to the negative t over tau. And then V equals V naught times 1 minus e to the negative t over tau. Okay, and so you have these two as well. I know I'm putting boxes around these, but I really don't think these are in your data booklets. I think you need to know how to derive them and get them that way, just so that you can. I did a horrible box around those, so I'm just switching that here real quick so I didn't swipe through it. There we go. Okay, so these ones are for growth. These ones up above are for decay. But it's just that you just take you take your exponential and do 1 minus it, and this is what you end up with. But you should be able to come up with that. Just think your way through it. I hate to add on more what to think. So what is this time constant? Why is it our time constant, and what does it mean? So this is the last thing we're going to do here in this video. I believe that's the last thing, unless I think of something that I've forgotten, but pretty sure this is the end of it. So let's look at this. What happens when the amount of time that has passed by is equal to the time constant? So let's say it's Q naught, right, Q naught e to the negative, and now what we're going to have is we're going to have tau over tau, right? So the amount of time that has passed by, this time in the numerator, is now equal to that. What is it we get at that moment? And if you check this out, this is Q naught e to the negative 1, and if you type that into your calculator, what you get is you get basically that e to the negative 1 is 0.37. You get Q naught times 0.37. And so what you see is that what this is telling you, so after time tau, after the amount of time of the time constant, 63% of the charge on the capacitor is gone. Because what you see here is we only have 37% of the original charge left. That means 63% of it is gone after R times C, or tau amount of time has gone by. Okay? So that's what the time constant tells you. It's the amount of time it takes for 63% of the charge on a capacitor to be gone. If you think about it, it also means it's the amount of time for 63% of the initial total current to be gone. So for it to have dropped 63% in current and 63% in voltage, because you can take the current and voltage equations here, right? and do the same thing. It's e to the negative 1, e to the negative 1. You get still 0.37s for both of them. So it's basically 63% of after time RC, 63% of the charge is gone. 63% of it's been a 63% decrease in current and a 63% decrease in voltage drop or voltage maybe supplied by the charge of the capacitor discharging. Okay, so yeah, that's that. If you can't remember what it is, just go ahead and plug this in and plug the e to the negative 1 in your calculator, and you'll get that, and it'll tell you immediately. If you can't remember, oh, was it like 64% or 53%, or you can't remember that percent, just plug it in, you'll get it pretty quickly. Okay? I think that's everything for this topic, and I think that ends our entire topic, unless I'm forgetting something, in which case I'll make another video to add that on. All right, that's all.